The systems driving our digital lives, from cloud computing to the AI on your phone, process billions of logical operations every second. It's an invisible speed we've come to take for granted. But that speed was unimaginable in 1822, when Charles Babbage first designed a machine that could automate calculation. This is his difference engine. It wasn't powered by code, but by the physical movement of these brass gears and levers. When Ada Lovelace studied Babbage's later designs, she wrote the first algorithms for them. She saw that if the gears were arranged correctly, they could be programmed to perform any logical task. Despite the brilliant logic, the engineering hit a wall. Mechanical parts were heavy, created friction, and relied on steam. A machine made of cogs could never move fast enough to run complex programs. Babbage and Lovelace had the logical blueprint for the computer 200 years ago, but they were trapped by the physical limits of metal and steam. To solve the speed problem, engineers in the 1940s stopped trying to move brass and started moving electrons. This shift led to ENIAC. It was the first large-scale electronic computer capable of general-purpose tasks that mechanical machines couldn't handle. ENIAC used these glass vacuum tubes to control electricity. Because electrons encounter almost zero friction in a vacuum, calculations happened thousands of times faster than any gear could spin. However, these tubes were fragile and generated extreme heat. To get enough power, you needed thousands of them, making the computer weigh 30 tons and occupy an entire room. Electrons solved the bottleneck of speed, but the size and unreliability of vacuum tubes meant computers were too massive and too hot to scale further. In 1947, Bell Labs invented the transistor. It was a tiny device that did the job of a vacuum tube, using solid materials instead of glass and vacuums. Transistors were smaller, faster, and much more reliable. They allowed computers to shrink from the size of rooms to the size of cabinets. But as computers grew more complex, engineers hit a new bottleneck. Every single transistor had to be wired together by hand, an impossible task once you needed millions of them. In 1958, Jack Kilby and Robert Noyce developed the integrated circuit, or microchip, to bypass the wiring problem. Instead of wiring parts individually, they printed entire circuits onto a single wafer of silicon. Thousands of components could now occupy the same tiny footprint. The integrated circuit meant computing power was no longer tied to physical bulk, allowing for decades of continuous miniaturization. By the 1980s, these chips became affordable enough to power personal computers in homes and businesses worldwide. Processing power continued to compress, moving from desktops to portable laptops that could be carried anywhere. But billions of these powerful machines were sitting in isolation. They could process data locally, but they couldn't share it. The internet revolution of the 1990s connected these isolated machines, creating a global network for data and communication. The computer's role changed from an isolated calculator into a gateway for a globally shared system of information. Today, the global network has evolved into the cloud. Massive data centers hold more processing power than Babbage or ENIAC engineers could imagine. Companies like NVIDIA and AMD now design specialized, hyper-dense chips capable of processing the massive amounts of data required for modern software. Developers at OpenAI use this hardware scale to train neural networks that recognize complex patterns and interpret language, achieving the logical depth Ada Lovelace first predicted. But we are hitting the limits of silicon. We have packed transistors so tightly that we are now reaching the scale of individual atoms. To move further, researchers are exploring quantum computing, looking for a new physical medium that can once again bypass the boundaries of standard hardware. It is a 200-year cycle of engineering, identifying a physical limit and finding a new material, from brass to glass to silicon, to overcome it. By systematically breaking these bottlenecks, we transformed the computer from a heavy mechanical calculator into the global engine of modern science and technology. We moved from a machine that counts to a tool that accelerates how we discover, build, and connect.